Chapter 5, we are continuing loops, and in particular, continuing for loops. Always fun for loops because they're super easy. So as mentioned, often you want to loop and you want to iterate a specific number of times. You want to use a counter to count those number of iterations. We've seen how we can do this with a while loop. We, in fact, have used a while loop to loop a certain set number of times. Nothing wrong with that. Hopefully you're comfortable with that. But in fact, there's a much easier way to have a counter-controlled loop, and for this, Python gives us a for loop. But first, revisit, this is the while loop structure of if we wanted to loop a certain number of times. In fact, what if I wanted to start I at 0 and say while I is less than 5, and let's do something it says here, the loop body, let's just say we only wanted to print I. No problem, we print, let's do it like this, print I is blank dot format, let's make it look nice, format I, and then what do we need to do? We need to update I at every single iteration. So update I, or let's say increase I by 1, so I plus equals 1. All of that is required to use a while loop as a count controlled loop. We first have to make our counting variable, in this case I. We need to have a condition. We want to loop as long as I is less than 5, and then finally we need to increment I. So when we run this code, sure enough, we get I is 0, I is 1, I is 2, I is 3, and then I is 4. Nothing wrong with that loop. But Python gives you a much easier way, this basic for loop. So check this out. All of that code can be effectively summarized using a for loop. For I in range 0, 5, and I'm going to take this print statement right here. And did I not copy it? Let's try that again. Copy, paste. These two lines of code are the same as all of that. That's crazy. And so that should impress upon you. Let's run this first so we can see it. Here we have I is 0, 1, 2, 3, 4. That's from the for loop. And then we have I is 0, 1, 2, 3, 4. That's from the while loop. So this should impress upon you that, wow, that's not only so much easier, so clear to understand, but just so much also shorter. So what does it impress upon you? That if you need to loop or to iterate a certain known number of times, that's when you use a for loop all day, every day. So the general syntax of a for loop is you have some variable in a sequence. And here the sequence is a range of values from 0 up to 5, but not including 5 as we saw on this example. And then you simply have what goes on inside the loop body. So this is revisiting, just as an introduction here, revisiting those same examples we ended up with last time. So if I said for I in range 4, 8, let's go code up some of these. For I in range 4, 8, what is it going to print? It's going to print I is 4, I is 5, I is 7, I is 6, and then I is 7. Let me get rid of the is. Let's make like a colon. I colon. So I is then 4, 5, 6, and 7. Notice we do not print the 8 because in fact, as we saw, that this effectively loops from that initial value 4 all the way to the ending value 8 minus 1. So we loop to 1 less than that final value. The other example, for Sarah in range 5. And as mentioned, this variable here, I, it's just the counting variable for this for loop. You can call it whatever you want, as I did there, as I called it Sarah. For Sarah in range, and I'll put here Sarah and Sarah. Here I have 4, 8, so Sarah is 4, 5, 6, 7. But now, what if I said just Sarah 8? What's going to happen? Just Sarah 8. It's going to loop, let me come up some. This is going to loop from 0 to 7. Right? So the assumption is if you only have one value inside these parentheses, inside the parentheses of that range function, if you only have one value, the assumption is that the starting point is a 0. So notice for Sarah in range, 0, comma 8. Here's the output. If I get rid of 0 and I do not specify the starting point, the assumption is that 0 is the starting point, so you don't even need to put 0, comma 8. No harm if you put it. It's the same thing, but you don't need to put it. I can get rid of 0, 8, and I get the exact same output. What if I said 0, 4? If I just put 4, this will print 0, 1, 2, and 3. Or if I had put 0, comma 4, it would give you the exact same output. Cool. What is another one? Or revisiting this, so now that we see that we can have one value inside that range function inside the parentheses, we can have two values. We also have possibly three values. So let's remind us of all three of those possibilities. In these values, they're called arguments. So inside the range function, we have those two parentheses, the pair of parentheses. Inside those parentheses, you can have one value, aka one argument, or even, again, aka parameter. Arguments and parameters, those are synonyms in code, not just in Python, in every language. We can have an argument or a parameter, those are synonyms. Those are the values that go inside the parentheses. So if we have only one value inside the parentheses, such as range 5, this assumes an initial value of 0. If you have two values inside the parentheses, such as 5 and 10, 5 is your initial value and 10 is your ending value, but of course we always go from 5 up to 1 less than that ending value. So in that case, it would go from 5 to 9. And then if we have three values or three arguments or three parameters inside those pair of parentheses, that third value is what? That third value is the step size. And the step size is assumed to always be 1 if you don't include that third value. So what do I mean by this? Let's come here from 0 to 10. We run it. So notice we go all the way from 0 up to 9. And the third value, which if you don't put it, just like remember, we don't have to put this first value. The assumption is 0. I can put the first value and it starts at 0. No harm if I don't put it. Well, in that same vein, or in that same way, I don't have to put a third value. But if I do not put a third value, the assumption is we have a 1. That right there, if I type that or I don't type that, it's the exact same thing. So here, without typing it, here with typing it, the exact same thing. What does this mean right here? It means go from 0 to 10 by ones. So start at 0, add 1 to it, now we're at 1, add 1 to it, now you're at 2, add 1 to it, now you're at 3. So your step size is 1. But notice when I make this a 2, now the step size is 2, and we started at 0, then we went to 2, then 4, then 6, then 8. Notice we don't even do 10 because we have to stop before 10. What if I made a step size of 3? 0, 3, 6, 9, or a step size of 4. 0, 4, 8. Let's loop up to 50. How about a step size of 10? This will be 0, 10, 20, 30, 40. So the step size is just how big of a step do you take at every iteration. When we don't put anything, the step size is 1. We literally, between every iteration, we just increase the counting variable. In this case, the counting variable is Sarah. Sarah starts at 0, then Sarah becomes 1, then 2, then 3, then 4, because there is no step size mentioned, and the assumed step size is simply 1. But if we make this step size 5, so now we're going to start at 0, and then go to 5, and then 10, 15, 20, all the way up to 40. What if I wanted to include 50? For whatever reason, if I wanted to loop from 0 all the way to 50, including 50, well, you simply need to go to 1 larger, right? Because you always stop at 1 less than. So here, it would go all the way to 50. I could make a step size of 10, for example, and that is what we would have. So that is that third parameter, that third argument, when you have a step size. Here we have for Mike in range 1, 10, 2, print Mike. And now we're looping starting at 1, going to 10, but not including 10, and the step size is 2. 0, 30, step size of 5 for Barbara. So Barbara is our counting variable. So we start at 0, and then we go to 5, 10, 20, 5, 10, 15, 20, 25, and we do not go up to 30. And then finally, we ended with this idea of counting backwards. How could we count backwards? If we wanted to, for example, if we wanted to loop from 10 down to 0 or down to 1, but including 1. So basically 10 down to 0. And with a step size of 1. So we really want to print what, for clarity? Print these values: 10, 9, 8, 7, 6, 5, 4, 5, 5, 4, 3, 2, and 1. We want to print those values. How can we do that? Well, let's do this one. For Katie and range. So what is the range going to be? Well, we're going to start at 10. That's easy. Start at 10. And we want to go down all the way to 1, including 1. So we really want to go down all the way to 0, right? Because we want to go one step farther. And what's the step size here? Well, the step size is 1. But if you just put 1, watch what happens. Nothing happens. Because you're saying go down from 10 to 0 with a step size of 1, so it's really stepping up. This is really trying to do 10, then 11. Well, you're never going to make it to 0. So it has to be a step size of -1. So that's going to bring you from 10 to 9 to 8 to 7 to 6, 5, 4, 3, 2, and 1. What if we had a step size of -2? This will bring us from 10 to 8 to 6 to 4, all the way down to 2. So that's how you count backwards, where you have the initial value is that larger number. The ending value should be, of course, smaller, and the step size is going to be negative. So from 5 down to 0, but of course not including 0, with a step size of -1, that's the output that we would get. So the summary that we ended with last time as well, which loop should you use? A while loop or a for loop, because each has a purpose. In short, when should you use a for loop? The answer is when you know how many times you want to iterate. If you know that I need to loop 100 times, that's when you do a for loop. If you want to loop 100 times, it's as simple as for I in range 100. Done. That would be so much more complicated to do that as a while loop. Now, at the same time, when should a while loop be used is when you need to loop an open-ended, an indefinite number of times, maybe based off of a user confirmation. Do you want another question? Yes, let's loop again. Do you want another question? Yes, loop again, right? In this case, you don't know how many times, so you cannot really use a for loop in an effective manner. For that type of problem, a while loop is perfect. So now we have some practice. Practice program 8 GCD. Write a program to ask the user to enter 2 positive integers. You should then find the greatest common divisor and print the result to the user. So as always, we have the problem-solving phase, then we have the implementation phase. Ask the user to enter 2 positive integers and find the GCD. So the first question is, for some of us, what is a GCD? Or another term is GCF, the greatest common factor. And all of a sudden you're like, no, and you're going back here. I'll let you cry with them. You're going back to your math, and you said he promised us no math. This is not going to be too bad. I promise this won't be too bad. The greatest common divisor, also known as the greatest common factor. So given 2 integers, the GCD is the largest integer that perfectly divides into both of the given numbers. So find the largest integer that divides into both of them. So for example, the GCD of 4 and 2 is clearly 2. 2 is the largest number that divides into 4. It's also the largest number that divides into 2. What about the GCD of 16 and 24? So you have to think about, okay, well, what are the possible integers that the largest integers that divide both into 16 as well as into 24. We see that if we come over here to a tablet, we can see that given, again, 16 and 24. If we just go through some integers, let's put some integers over here on the left. 2, 3, 4, 5, 6, 7, 8. Does 2 divide 16 and 24? If you take 16, divide it by 2, yep, the answer is 8. It divides it perfectly. Does 2 go into 24? Yeah, the answer is 12. Cool, so 2 works. Let's put a little check mark there. Check mark. 2 works. What about the number 3? Does 3 divide into 16? Nope, it doesn't. So you don't even have to look at the 24. 3 does divide into 24, but there's no need to even look at it. So 3 does not work, right? Let's get rid of this. 3 does not work. Get rid of 3. What about 4? Does 4 divide into 16? Yes, it does. Does 4 divide into 24? Yes, it does. Cool. 4 works. Then we check 5. Does 5 divide 16? The answer is, I did a little mistake there. Does 5 divide 16? No, it does not. So 5 does not work. Then we check, does 6 divide 16? No, it does not. That doesn't work. Does 7 divide 16? Nope. Does 8 divide into 16? And the answer is yes, it does. Cool. So now let's check 24. Does 8 divide into 24? The answer is yes, it does. The answer is 3. So now we have that 7 did not work, 8 works. And in fact, you have to keep checking all the way up to the smaller of those two numbers. So you would have checked 9 and 10, 11, 12, 13, 14, 15, and checked 16. And you would have seen that 9 doesn't work, right? 9 doesn't work, 10 doesn't work, 11 won't work, 12, 13, 14, 15 doesn't work. 16 divides into 16, but it does not divide into 24. So what was the largest number that divided cleanly into both of them? The answer was 8. And so 8 would be the GCD. So the GCD of 16 and 24 is absolutely 8. What's the GCD of 25 and 60? The answer is 5. So now say, cool, are we ready to code? People always want to start coding immediately and skipping the problem solving phase. The answer is no. We want to think a bit more about the problem, understand that solution perfectly before we try to go calculate that GCD. So given these two values, let's call it N1 and N2, consider the fact that 1 is going to always be a common divisor, right? You can divide 1 cleanly into both of those numbers. But is 1 the greatest common divisor? You don't know. So you need to do what now? Check the next number, 2. Does 2 divide cleanly into both of them? Maybe it does, maybe it doesn't. Then check the next number, 3, 4, 5, 6. You want to keep going and checking all numbers to see if they cleanly divide both N1 and N2. And any time you have a new number that cleanly divides both of them, say, yes, that's my new greatest common factor or greatest common divisor. So check the numbers 1 by 1 by 1. And how, of course, do we check if it cleanly divides? By using, of course, mod. I think we're good there, but let's just go here and confirm. Let's erase all of this. Right, so if we want to check, does what? 4 divide 16, right? We want to check over here, for example, that last problem, does 4 divide 16? How would you have done that? The answer is we know that 4 divides 16, and because there's no remainder of 0, or there is no remainder, the remainder is 0. So how do we do that? We say 16 mod 4, does it equal to 0? And if it does, then we know, all right, that works. 4 cleanly divides 16. What about 24? You would have said 24 mod 4. Does that equal to 0? Yes, it does. The answer was 6 up here, but when we did it, we got a remainder of 0. So that one worked perfectly as well. So we use mod to confirm that there's no remainder when we're performing these divisions. And so keep checking all of these numbers, 2, 3, 4, 5, 6, all the way up to the smaller of N1 or N2. And anytime you find a new number that divides both N1 and N2, then you have a new GCD. So now we're ready for the implementation phase. Let's go try to code this up. Here's the output. We ask the user to enter the first integer. We ask the user to enter the second integer, and then we're going to print the greatest common divisor for those two numbers is something. So let's code this up. So new save, let's call this GCD program. GCD program. And let me zoom in a bit. All right. So we want to do what? We want to ask the user, enter the first integer. So let's call it num1 equals int input, enter the first integer. Num2 equals int input, enter the second integer. And then ultimately we really want to print down here at the bottom, print the greatest common divisor, I'll just call it the GCD or GCF of blank and blank is blank. Dot format, num1, num2, GCD. Cool. That's what we want to print. So we're ready to print that, except we don't have this value GCD. So what did we say we can assume the GCD at the very least? If I said find the GCD of these two numbers, of how about 3 and 7? What's the GCD of 3 and 7? The answer is 1. There's no larger number that divides both 3, no larger integer that divides both 3 and 7. So the answer is 1. So we had said start the GCD at just 1, and then we're going to test all numbers starting from 2 up until the smaller of these two numbers. But let's remember that loop design strategy where it says code it one time. So we will have a number that we're going to, we said start at 2, and let's call this candidate, or let's call it possible GCD. Possible GCD equals 2. And here I would say if num1 mod the possible GCD equals 0 and num2 mod the possible GCD, if that also equals 0, right? So I'm trying to take this possible GCD, which is 2, and I want to divide num1 by 2 and check its remainder, which is what this is doing. If the remainder is 0 when we divide num1 by possible GCD, and if num2, when we divide it by the possible GCD, if it's also equal to 0, guess what? We found a new GCD. So GCD equals possible GCD, right? I'm going to put a comment here. So save the possible GCD as the new GCD value. Let's put a comment for this if statement. So if num1 and num2 are both divisible by the possible GCD, that's what we're checking here. If num1 mod possible GCD is 0 and num2 mod possible GCD is 0, that means we found a new one. So let's set our GCD equal to that possible GCD. So now it would have been 2. And we want to keep doing that over and over, because remember, the loop design strategy is code it once. Well, that's the one time. But now do what? Do it over and over and over. And so what do we want to do here is we want to wrap this inside a while true, and we'll ignore what is the condition of exiting. Let's tab this over. So we check this value, and after we check it, what do we need to do? We need to increment possible GCD. So now update or increase possible GCD by 1 for the next iteration. So we just checked possible GCD is 2, and now check 3, and then 4, and then so on. So here, possible GCD plus equals 1. Let me scroll this down, clear this out, zoom out just a little bit. So while true, if both are divisible by the possible GCD, we found a new one, update it, and then simply check the next one. Do this again and again and again. Now, of course, if I run this code, enter a number, let's say we enter 8 and then 24, it never stops because it's a while true. This is an infinite loop. So now how do we stop? We said we want to loop until the smaller of those two numbers. So while the possible GCD is smaller than num1 and while also smaller than num2 would be a good condition. So while possible GCD is less than or equal to num1 and possible GCD is less than or equal to num2. Keep looping while both of those conditions are true. And once it reaches the smallest of those two numbers, it will then exit the loop. So here when I run this code, not debug it, let me hit run. When I run this code, we enter 8, we enter 24. The GCD of 8 and 24 is 8. Let's pick another 2. Let's run this code. Let's do, how about 16 and 4? The GCD of 16 and 4 is 4. Let's do something more colorful. How about 80? No, I don't like 81 either. Let's do 110 and what? 110 and 48. The GCD of 110 and 48 is 2. That wasn't very exciting either. I'm trying to get a good multiple. 64 and not 20. Let's do 64 and 48. The GCD of 64 and 48 is 16. So the program's working as expected. Let's now go look at what we have in the slides, see how this differed. So here we started the GCD at 1, because at the worst case scenario, if we run this code with the GCD of, let's say, these two numbers, 3 and 7, well, there's no greater number than 1 that divides both 3 and 7. So you want to start your GCD at just 1, and we never improved it. So we never improved it here with one of the possible GCDs, which would have in this case been 2 or 3. We never improved it because neither 2 or 3 were divisible cleanly into those numbers. So the GCD of 3 and 7 is simply just 1. And this matches here. So it does say try recoding this as a for loop. Think of what you could change to code this up as a for loop. So let's see if we can just very quickly modify this code and make this as a for loop. Here, instead of a while loop, we want to put a for possible GCD in range. So I want to use this exact same variable name because we want to loop over a certain number of possible GCDs. For possible GCD in range 2, something. We want to go up to some number. What number do we want to go up to? We said the smaller of those two numbers. So here, let's just say I'm going to make a new value. How about smaller number equals the min of num1, num2. That's going to be the smaller number, just using the built-in min function in Python. So from 2, up to the smaller number. And I could have simply put this right here. Now that's not going to go up to and including that smaller number. So if num1 is 4, num2 is 8, this is really going to say 2, 4. And we really want to go up to 4 including 4. So you really want to do 4 plus 1, right? So here I could have just done smaller number or min num1, num2 plus 1. That's going to be the exact same for loop. And so some people may not like all of this right here, which is why I had offloaded this into a variable smaller number equals that. And so now I can just put this here if you prefer. So this I want to confirm. So now I no longer need to increase the possible GCD by 1 for the next iteration because that's automatically happening right here by the step size of assumed to be 1, or I could type it manually. So now, once again, let's run this. Enter the first number, 8, second number, 24. The GCD of 8 and 24 is 8. Run it again with those other two values we had, 64 and 48. Nope, wrong. 64 and 48 is GCD of 16. Cool, that was GCD. Another one, table of square root values. Write a program that prints out a table of square root values using the square root function. It's actually going to be pretty easy. This is not math. So problem solving phase, here's the sample on the right. We basically want to come up with that exact same program or output. So just analyze that very briefly. How many iterations? We want to loop from 0 all the way up to 20, including 20. So let me make a new program, file, new, save, print, square, or let's call it square root table, square root table. And what do we want to do? We want to loop all of those times from 0 up to 20, including 20. Of course, we need to import math to use that square root function. We want to print that header row, and then we just want to print the data at every iteration of the loop. So let's start by importing math. Import math. Before looping, print the header row, right? Which is basically print this word number followed by this square root. Let's use formatted printing. So let's try to guess how many spaces. 1, 2, 3, 4, 5, 6. It looks like it's going to be another 6 more plus maybe 2. So I'll assume 14 spaces. So print, we want to print basically two things inside here, right? We want to print two strings. Here's a string and here's a string. So I'm going to put two placeholders back to back. This first placeholder, I want to do what? I want to print inside it. So I'm going to go ahead and put a dot format. I want to print what? The word number. And the second placeholder, I want to print square root with a capital R. And so if I just run this code, of course, it's going to print it back to back, number square root. That doesn't look pretty. So now we need to put in some formatting. So this is a string, so it's :S. We want it left aligned, and we said 14 spaces. And this is :S, and let's left align it. And as you know, I don't need to specify the number of spaces because there's nothing coming afterwards. That looks pretty good. So now loop 21 times and print the square root values. So here we're going to do a for loop for I in range 0, comma. We want to loop all the way up to 20, including the 20. So we're going to say 0, comma 21, step size of 1. As you know, we don't have to put the step size of 1, but why not if you want to just see that third parameter, that third step size. And so what do we print inside here? Well, since we already have this print statement perfectly formatted, I'm going to use it. Now here, what goes inside this we'll talk about. But what do I want to print? I want to print an integer here. And then here, I want to print a double with a floating value with 4 digits after the decimal. So this is going to be 14D for integer. And this is going to be F, and it's 0.4F. 0.4F. Now, what do we want to print? Well, this is merely printing the counting variable from 0 up to 20. What is the counting variable? It's just I. We want to print I. And what do we want to print right here? The second thing gets printed. What is that? So when we print 4, we should print 2. When we print 16 here, this should print 4.0. What is that? It's the square root of I. So instead of I, it's going to be math.sqrt of I. And that's it. We run the code, and here is our result. We have the exact same table. So the purpose of this problem was not about the square root. It was really just to recognize that, hey, I see that I want to loop 21 times. Because of that, let's just do a for loop. That's really the takeaway of that problem. All right, about 5 or 6 minutes left. an introduction to nested loops. Well, just like selection statements, you can have if statements inside other if-else statements. Well, loops can be nested inside other loops. That first loop is considered the outer loop, and then inside this outer loop, we can have more and more nested loops. And yeah, at the beginning, in fairness, this is a bit confusing, but it's going to be okay. Each time the new outer loop starts again, the inner loop, or each time the outer loop goes to the next iteration, that inner loop is restarted and begins anew. So here's just a nice small example that's worth looking at. For I in range 1, 3, how many times does that loop iterate for I? It's going to loop 3 times, right? For I in range 1, 4, I becomes 1, I has the value 2, I has the value also of 3. It will loop 3 times. But for each of those times, check it out, when I is 1, well, what happens inside the loop? We're going to print we have another loop for j in range 1, 4, and now we print this. So let's go over here and code this up. Let me come back to the for loops, delete this, and for I in range 1, 4, and let's print out something similar. Print, what do we have? We have I colon this dot format I. What happens here? It's going to print I is 1, I is 2, I is 3. But now check this out. If inside here, if I say for j in range, it's a different variable, 1, 4, and now let me indent this over. I'm not going to change my print statement, but let's just run it as is and see what we get. Notice we print I as 1 3 times, then we have I as 2 3 times, then we have I as 3 3 times. Well, what's going on? Well, I becomes 1. It's better just to debug this. And when I debug it, let's step through. This is going to be F7. So I is 1. Let's look over here at the variable. I is 1. And now we come inside here. We're at this for loop. For j in range 1, 4. So now j has the value of 1. And we print I. We print the value of I, which is just 1. Well, now j is 2. And we're going to print I as 1. And now j is 3. And we're going to print I as 1. And when we print I as 1, remember, we're still at the value, I is still 1. On this outer loop right here, I never became 2 yet. I is still 1. And we simply looped this inner loop. We iterated it 3 times. So after iterating 3 times, this inner loop has completed. And so now we come back to this outer loop, and guess what? I now becomes 2. If you look over here on the right side, I is 2. And now that I is 2, guess what? We repeat all of this. For j in range 1, 4, j is 1, I is 2, we print I. Now j is 2, we print I again. Now j is 3, we print I again. And now I becomes 3, and we do this inner loop 3 more times. And so a better way of really seeing what's going on here is to add something to this print statement. Not just to print I, but to print the value of j. Let's do this, and then say right here, j colon curly bracket format ij. So when we run this now, let's debug it. First, let's run and make sure we got what we want. Cool. So when we debug this and you step through, I starts at 1, j starts at 1, so we print I and j, and we get 1 and 1, and this is the output as we expect. Well, now j becomes 2. I is still 1, but j is now 2, and we print this, so we get I is 1 and j is 2. Remember, this outer for loop up here, I is currently 1, and we're simply iterating now the inner for loop. J was 1, then j was 2, now j is 3, and we're printing this output, I is 1 and j is 3. Well, now that we've looped from j in range 1 all the way to 4, but not including 4, from j from 1 to 3, now that we've done that and finished it, Now we go back to the outer for loop and we finally increment I, and I becomes 2. And now that I becomes 2, we loop again on the inner loop. I is 2, j is 1, I is 2, j is 2, I is 2, and j is 3. We go back to the outer loop. The outer loop, we have I is 3, j is 1, and then we do the inner loop, j is 2, and j is 3. That's a lot. And we realize quickly that we can iterate. We can get a lot of iterations really quick. What if I did 1,000? I'm sorry, 100. Let's do 1,000 and 1,000. 1,000 and 1,000. How many iterations is going to happen here? We're going to loop 1,000 times on that outer loop. And for each one of those times, the inner loop is going to loop 1,000 times. And here the bottleneck is just the output, because output is slow in Python. But notice what's going on. It's great. We can now, I think, get a good visual. I is currently 2. We're looping from 0 to 1,000. Now I is 3. We're looping from j from 0 to 1,000. Now I is 4. And you see it looping from 0 all the way up to 1,000. We're not going to watch this whole thing because I is only currently, 6? 6 goes from 0 to 1,000. Now I is 7. 7 goes from 0 to 1,000. That is going to be a lot of iterations. So a short amount of code, but we just asked Python to do a lot of stuff. Or here, let's check this out. What if I said count equals 0? And here, instead of printing, if I said count plus equals 1. What is count going to be if I print count right now? Take a guess on what you think count's going to be. How many iterations did we go through? And the answer is 1,000,000. And notice, so it prints that very quickly. So the bottleneck on the last example was the output. It's slow to print output to the screen. But here we just iterated 1,000,000 times, and Python counted, it incremented count by 1 at every single iteration. You want to loop here, instead of 1,000,000 times, how about 100,000,000 times? Takes a little bit longer. Let's see, I'm going to wait 5 more seconds. 1, 2, there we go. We got our answer. 100,000,000 times we just iterated. So a short amount of code, a lot of executions. So that is the idea of nested loops. We're going to end by simply tracing through this example to give you an idea of a better understanding of really how nested loops work. So here we have a for loop for I in range 1, 5. Ask yourself how many times that iterate. It iterates 4 times from 1, 2, 3, 4, but not when I is 5. So I is 1, 2, 3, 4. We're going to iterate 4 times for the value of I. And inside that for loop, we have this j variable, which we initialize to 0. And now we have a while loop. So let's start this out. I is 1. And j starts at 0 while j is less than 1. J is less than 1 because j is 0. What are we going to do? We're going to print j. So we print 0. And we will print on the same line because of this end equals. And now we're going to add 1 to j. When we add 1 to j, remember j is 0, so now j becomes 1. While 1 is less than 1, that is now going to be false. This while loop will finish, and we come back up to the for loop where I was 1, now I is 2. We see here I is 2. J is back to 0 again. While 0 is less than 2, print j, so print 0. Increment j, j becomes 1, so now I is still 2 and j is 1. Is 1 less than 2? It is, so print j, which is 1. And now add 1 to j, j now becomes 2, and 2 is not less than 2, so this while statement is now false. And now we come back up to I becomes 3. J is 0 less than 3? It is. Print j, which is 0. Increment j, j becomes 1. Is 1 less than 3? It is. Print j, which is now 1. And we increment j to now 2. So now we're at I is 3 and j is 2. Is 2 less than 3? It is. Print j, f2. Increment j to now 3. While 3 is less than 3, that is false. Right? J becomes 3. 3 is not less than 3. That's false. We finish this while loop. We come back to the for loop. I is now 4. J is once again 0. Is 0 less than 4? That's true. We print J, which is 0. We increment J. J becomes now 1. Is 1 less than 4? It is. So we print 1. We increment J to 2. Is 2 less than 4? It is. So we print 2. We add 1 to J. J becomes 3. Is 3 less than 4? It is. We print J. We print 3. And then we add 1 to J, and J becomes 4. 4 is no longer less than 4. We exit the loop. That's a lot. To be very clear, that is a lot. I won't repeat that, but for those who need to see that again, no problem. Rewind the video, watch it again. That's a lot. As a preview, we will have several more of these tracing examples because we've mentioned it's a skill to be able to look at code and trace through it. That's already challenging enough with regular for loops, with regular selection statements, even nested selection statements. But now when you have nested loops, for loops inside for loops, or while loops inside for, or for loops inside while, it can get messy and it takes practice. So if you're looking at this and you feel maybe a little bit sad or concerned or other thoughts, all of that is okay as long as we practice. So rewind, take a look at that again, and rest assured that we're going to see several more examples. It's been fun. As always, reach out, ask questions, leave a comment. Take care.